Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll introduce you to the framework that we will use for analyzing data this semester. This topic is introduced to you in your textbook in Chapter 1. When we conduct data analysis, we are trying to create a representation of the data. We can use the basic equation data equals model plus error to conduct many different types of statistical analyses. Data refers to the collected data from a research study, that is, the actual scores or observations. A model is a representation of the data, and model refers to a summary of the data, or a representation, that is used to make a prediction about each score in the data. Error encapsulates the part of the data that the model fails to represent. Error is also known as residual, as in the residual or leftover part of the data that is not predicted by the model. It might help to visualize what this means. There's a scatter plot. Here's a scatter plot of some data for two variables, height and weight. You can see here that height is on the y-axis and weight is on the x-axis. We can see that there's somewhat of a positive relation between height and weight. The scores that are lower on height are generally also lower on weight, and the scores that are higher on height are also generally higher on weight. These scores, or the dots on the plot, are the data. I've drawn an arrow to a sample data point here. Now, if I wanted to draw a rough representation of this relation on the plot, I could draw a line through the data points that indicated the trend of the data. This line, which slopes upward, could be considered a model of the data in that it's trying to represent the relation between height and weight for this particular set of data. But we can see that not every data point lies on the line that I've drawn. So obviously, this model doesn't represent exactly what's happening with the data. In fact, almost none of the data points lie directly on the line that I've drawn. The space between each data point and the model line is the error. Error, it's the extent to which the model does not fully represent the data. So here I've drawn a line that kind of indicates the space between the model line that I've drawn and the sample data point that I've highlighted. That's the error, that distance between the line and the data point. Let's shift this simple equation around a bit. If we subtract error from both sides of the equation, we see that the model is equal to data minus the error. Our goal is always to build the best model possible. That is, to find the model that represents the data best. Imagine if we had a model that perfectly represented the data. In the formula above, model would equal data, and there would be no error. In the real world, it's highly unlikely that we can ever find a model that perfectly represents our data. Thus, because we accept that there will be some error that the model doesn't represent, our goal of data analysis is to find a model that represents our data best by minimizing the error. However, we could make an extremely complex model that would predict our data perfectly, but it wouldn't generalize to any other situation and therefore wouldn't make a good model for theory advancement. In science, we always try to find the simplest model that fits the data well, but not perfectly. Therefore, a second conflicting goal of data analysis is to find the simplest model that fits the data. Let's focus on goal number 1 for a minute. How can we reduce error in our data? One way would be to improve our research designs. If we can control all of the environmental factors in a study, ensure random sampling and random assignment, and make sure every participant receives the experiment in the exact same way, we should theoretically have less error in the data. But most of the time, we do the best we can, and when it comes time to conduct data analysis, the study is over and it's too late to control these factors. So for data analysis, one way we can reduce the error in the data is to include more information in the model. More on this in the next lecture. This concludes the first lecture, introducing a new data analysis framework. In the next lecture, I'll continue discussing this framework.